As Earth's plates diverge, collide, subduct, and slide past each other, oceans open and close, continents reassemble, and earthquakes, volcanoes, and mountains heave the crust, all of which bring together two key physical geography players: global tectonic systems and climate systems. Especially through weathering, which is when rocks break down by physically disintegrating or chemically decomposing. The weathering process actually removes carbon dioxide from the atmosphere by converting it into chemical compounds called carbonates that can be dissolved in water and eventually turned into rock. And young mountains like the Himalayas, which formed just 40-ish million years ago, seem timeless, but they actually weather and erode quickly, which might affect the balance of the Earth's systems. In fact, some geomorphologists who study landform and surface processes that shape the Earth think that weathering of the Himalayas when they first rose, along with the Rockies and the Alps, affected the atmosphere enough to change global climates. Of course, flattening entire mountain ranges happens over millions or tens of millions of years, but we can still see weathering in action. At timescales you and I can comprehend, weathering lends that reddish-brown tinge to my bike left outside and eats away at the facades of old buildings. But no matter where we look, weathering is the first essential step in wearing down the landscape, shaping the Earth slowly but surely. I'm Alize Carrere, and this is Crash Course Geography. Like we learned a few episodes ago, the Earth's topography, or the shape of the land, comes from a whole bunch of different processes, some that originate inside the Earth and some on it. And the rock cycle, which is the continuous creation and destruction of rocks and minerals, is driven by both those internal, or endogenic, and external, or exogenic forces. Many rocks form under high temperatures and pressures deep in the Earth's crust. And when they're exposed to the lower temperatures and pressures at the Earth's surface and all the air, water, and organisms, they start to decay, which is just part of the rock life cycle. Though each of the three rock types have distinctive characteristics based on their formation, all rocks eventually break down into finer material, which is where weathering comes in. Weathering breaks down the rocks and creates fragmented materials or sediments, which become the raw material for other rocks and for the formation of soils. So one reason why weathering is so important is because it's the principal source of inorganic material in the soil, which vegetation needs to grow. If it weren't for weathering, the Earth's continental surface would just be solid bedrock. Now, once those sediments are created, they're often picked up and moved somewhere else by wind, running water, ice, and waves. And we have a different word for that process: erosion. So we can think of weathering as prepping the rock materials to be moved, and erosion is when the rock actually gets moved. Both make up the first stage of denudation, which is the general word we use to talk about all the processes that wear away the landscape. Though sometimes, the weathered rock can move without the help of an erosional agent like water. Like, we call the pieces on the top of solid bedrock that haven't moved yet the weathered mantle, and it might just stay where it is. Or gravity could make it creep or slide or slump or flow downhill, which we call a mass movement. These are the mudslides, debris flows, and landslides we hear about that can be really dangerous and often become headline news. But before any transport can happen, from gravity or erosion, the land has to actually be broken down through one of three main types of weathering. Basically, we have to think about how rocks can break. So let's start with using just water. When water turns into ice, it actually increases in volume by 9%, which is how your water pipes can burst when it gets really cold. The pressure builds up and phew, the same thing happens in a rock. Water that's been absorbed into the pores within the rock expands when it freezes, building up stress and causing the rock to break. This is frost action, which can break off anything from small grains to large boulders, and is an important process in cold environments where freeze-thaw cycles are common. The debris that comes from frost action has a special name too. We call it scree, and we can find it at the base of cliffs in mountain ranges like the Alps and Rockies. Rocks can also get roughed up in coastal and arid environments and during dry weather periods when there's a lot of evaporation through salt crystal growth. As water evaporates, crystals can grow from the minerals that were dissolved in the water. The crystals fill up the pore spaces and other gaps in the rock and exert pressure, which forces apart mineral grains. When they fall out of rocks like sandstone, we call this granular disintegration. Like in Arizona's Canyon de Chelly, we find villages built into cliffsides used by the ancestral Pueblo culture about 1,000 years ago. These cliff dwellings protected them from the elements and from enemy attack, and were a whole web of interconnected residences and ceremonial centers located in deep indentations formed in the sandstone cliffs. The weathered niches were partially formed by salt crystal growth. So whether rock is weathered with salt crystal growth or frost action, or other processes we won't get into like thermal weathering, unloading, and slaking, when rock breaks down into progressively smaller fragments without being altered by chemicals, it's called mechanical weathering. Ultimately, mechanical weathering is what turns solid rock into regolith, which is the important bottom layer of soil profiles, and it also helps our next type of weathering by providing more surface area for weathering processes to operate. So let's talk about that bike I left out overnight, or maybe actually many days. The reddish-brown tinge on it is from oxidation, which is when certain metallic elements combine with oxygen to form oxides. The iron in my bike frame is being drawn out to form iron oxide, or rust, weakening it. And the same thing happens in rocks. When oxygen dissolved in water comes into contact with iron in a rock, the iron is removed, weakening the structural integrity of the rock. This is a form of chemical weathering which occurs when some or all of the minerals in the rock are altered or decayed by agents like water, oxygen, carbon, and other organic acids. We humans have actually contributed to a lot of chemical weathering, like on the columns of the Parthenon, which is a temple dedicated to the goddess Athena that stood for over 2,500 years on the Acropolis of Athens, Greece. Now there's a black crust on the columns from sulfur dioxide getting released in the air from burning coal in power plants, smoke emissions, burning oil, and other industrial processes. Add a little moisture, and that sulfur dioxide forms sulfuric acid that corrodes certain stone surfaces. But there's plenty of chemical weathering that happens without us, too. Water is the universal solvent, meaning it can dissolve almost anything, which can then get absorbed into a rock, so it's very efficient at chemical weathering, especially combined with carbon dioxide to form the chemical compound carbonic acid that dissolves many minerals and forms carbonates in a process called carbonation. This is the same process that gives the zing and sparkle to fizzy beverages, and even forms caves. Carbon dioxide dissolves in rainwater, and especially in humid climates, there's a lot of carbonation happening in rocks like limestone, where the main mineral making up the rock is calcite or calcium carbonate. Calcium carbonate reacts with carbonic acid to form calcium bicarbonate, which can be dissolved away in water. So just like oxidation weakened my bike frame, carbonation weakens the limestone. And when entire regions are composed of limestone, and there are a lot because there's a lot of limestone on Earth, it creates karst topography, which is where the caves come in. The word karst comes from the Karst Plateau in Slovenia, where this particular landscape was first described. Though you can also find karst scenery in southern China, Japan, Puerto Rico, Cuba, and the Yucatan Peninsula, as well as in US states like Kentucky, Indiana, New Mexico, and Florida. In a karst area, streams on the surface get diverted underground through openings in the rocks created by carbonation, which creates disappearing streams and dry valleys. There can be steep-sided gorges pitted with cavities called sinkholes, which can often collapse catastrophically. When cavities in the rock get large enough for humans to enter and explore, they officially become caves. And if they're formed by limestone rock, we call them solution caves, which usually form between two different rocks, like limestone and shale. As we enter a solution cave to go spelunking, or cave exploring, we're kind of entering a subterranean world that only exists because of chemical weathering. We might see sediment from glaciers mixed with bones of dead animals or even humans. And if we're lucky, we might see artifacts like pottery sherds and spearheads from the Neolithic, Bronze, or Iron Ages. A little further in, we might walk into a roughly dome-shaped chamber large enough to hold a tall building that was probably hollowed out by meltwater streaming through the cave at the end of the last ice age. Next, we find ourselves in a narrower passage and see beautiful and delicate formations called stalactites growing down from the ceiling. They're usually made of calcium carbonate that got weathered, then carried and deposited by groundwater one drip at a time from cave ceilings and walls. The similar-looking deposits growing from the floor are stalagmites. Depending on how fast the water drips, how many minerals the water contains, and the cave atmosphere, they can look more like columns or cones. And where a stalactite joins a stalagmite, we get a column. Many stalactites, stalagmites, and columns get stained beautiful colors as iron and manganese are oxidized through oxidation. Moving through the cave, the wild scenery isn't the only difference we notice from the surface. Caves are also unique habitats with fragile, self-contained ecosystems with simple food chains and a distinct climate. For instance, bacteria down here can synthesize inorganic elements in total darkness, unlike plants on the surface, and produce organic compounds that feed other cave life, like algae, small invertebrates, slimy salamanders, fish, and bats! Caves can be just a single passage a few feet long, or a large, multi-level, extensive maze. Mammoth Cave in Kentucky in the US is the longest in the world with over 640 kilometers of mapped subterranean hollows and passages. And worldwide, it's estimated that 90% of possible caves lie undiscovered. Which might not be all bad, since cave tourism is seriously impacting these otherworldly places that took millions of years to weather. So when we emerge from our cave tour, we have to take precautions, like being careful to not reuse our gear in other caves without extensive decontamination, or even at all to avoid the spread of white nose syndrome, a fungal disease killing bats in North America. Finally, the action of animals and plants bring about biological weathering that helps both mechanical and chemical weathering. Like the teenage girl in Harbin from episode 3 who almost twisted her ankle on the curb while jogging. It might have been that the curb was uneven because the tree roots exerted pressure to heave the sidewalks. Other organisms bore into rocks, and bacteria, algae, fungi, and lichens can chemically alter minerals in rocks. When dead lichens leave dark stains on rocks, these spots can absorb more thermal radiation than on lighter rock, which encourages weathering. And we can't forget us humans, who have exposed bedrock by building quarries, mines, roads, and railways. And our agricultural practices have greatly changed soil and weathering processes in many regions throughout history. Weathering is a complex phenomenon, and there are no firm rules as to how different rocks will weather in different climatic conditions, because minor differences in their characteristics and how much moisture is available can also control outcomes. But weathering itself doesn't work alone, and depends on other processes to transport sediment and expose fresh rock. On a hill slope, the processes of weathering, transport, and erosion are very much mutually interdependent and form one unified system shaping the Earth, which we'll continue discussing next time when we talk about erosion and how rivers shape our landscapes.